Okay, I don't know what the noise I made the first time was, but we're going to go through this math. So, skier is going down a hill. She goes down a vertical height of 200 meters. So I shall pop in that my height is equal to 200 meters and that the skier has got a mass of 65 kilograms. Calculate the change in gravitational potential energy. EP is equal to I don't know how many joules, taking the gravitational field strength to be 10 newtons per kilogram. Now, unless you say otherwise, always say it is 10 newtons per kilogram. EP is equal to M times G times delta H, which is equal to 65 times 10 times 200. Now, at this point, I have gotten at least 1 mark. Something I've done here will get me 1 mark. So that when I go to do my calculations, to putting in my numbers into my calculator, which I conveniently put behind me, I can get 65 times 10 times 200, the answer of 130,000 joules. Now, let's say you write the correct answer in here, and you write the incorrect answer in here. This is the answer that's always given priority. So make sure that this answer is correct. At the bottom of the slope, her speed was 36 meters per second. I'm going to say that her velocity was equal to 36 meters per second. Calculate her kinetic energy, EK, is equal to I don't know how many joules at the bottom of the slope. Now, what we can't, obviously we're missing something here. So it's only given us 1 number in this portion of the question, but remember this is part 2 of this whole question, and they've already given us her mass up here. So to find the kinetic energy of a person, it is 1/2 times mass times velocity squared. I can use the same mass from the top of the question as I can in the next section. So I'll say that my mass is equal to 65 kilograms. Then I put my numbers in. EK is equal to 1/2 times the mass, which is 65, times the velocity squared, which is 36 squared. Please don't forget to square that. It's a really common mistake that people make, and I really don't want you to do it. Pop that into my calculator, 0.5 times 65 times 36 squared, giving me an answer of 42120 joules. And my units match. There's nothing crazy going on there. I don't have to do any conversions, so I shall just carry on. A javelin has got a mass of 0.8 kilograms. Mass is equal to 0.8 kg. In one throw, the javelin left the athlete's hand at a velocity of 25 meters squared. Velocity is equal to 25 meters squared. Meters per second, not meters squared, meters per second. That's mistake number 1. Calculate the kinetic energy of the javelin as it leaves the hand, and I don't know how many joules. Write down my equation. EK is equal to 1/2 times mass times velocity squared. Put in my numbers. Times 0.8 times 25 squared. Pop that into my calculator. 0.8 times 0.5 times 25 squared. Give me a round answer of 250 joules. Mistake number 2, joules. Nothing weird. I don't have kilometers. It's kilograms, so my base units are right, so I can carry on. State the amount of work done by the athlete on the javelin as it gets to get it to a velocity of 25 meters per second. So the chemical store inside the athlete's arm was transferred by forces to a kinetic energy store in the javelin. The transfer of this amount of chemical store, the amount of energy that it had in its kinetic energy store was 250 joules, which means I had to have had 250 joules at least of chemical energy in my hand, and the forces will have transferred all of that energy to over there. The work done is the same as the energy transferred, so I can just copy down my answer, 250 joules. The next question, I'm going to find the mean. So to find the mean, the equation is something like this, and it's the sum of the numbers divided by the number of numbers. All right, but that doesn't really matter, and that's not this equation that you need. It looks something like that. So I'm going to add up all my numbers. I'm going to make them know what I'm doing. 17.5 plus 16.1 plus 19.4 plus 18.6 plus 20.2 divided by the amount of numbers 1, 2, 3, 4, 5. Now, any in here obviously anomalous? 1 away from that, 3 away from that, 1 away from that, 2 away from that. No, not really, so I can just use all these numbers. Now, fun fact, this will be completely discounted. I wrote some numbers outside of this gray line, which means it won't be picked up in the scanner. So if I mess up my calculations, then I'm not going to get any marks for trying. So please make sure that you don't do that in the real thing. Popping those into my calculator, my answer is 18.36 centimeters, but it is asking me to give my answer to two significant figures. So I'm going to count one significant figure, two significant figures, and return this as 18 centimeters. Now, I didn't have to convert these from centimeters into meters because the units I was asked for was centimeters. So we're happy days. Calculate the average time for the left hand. Use the equation time squared equals distance over 500. This is my left hand. This is trial 1, 2, 3. The distance dropped, meaning the average distance dropped was 14 centimeters for my left hand. So I shall write down that distance is equal to 14 centimeters. And my equation is t squared is equal to d over 500. I'm going to rearrange that to find that time is equal to square root of distance over 500. I'm going to pop in my number, that is 14 divided by 500, and pop that into my calculator, giving me an answer of 0.17 seconds. You can, if you want to, write down 0.1673 seconds if you want to, but usually when they give you something in 1 or 2 decimal places, it's good to give it back in 1 or 2 decimal places as well. All right then, next question. A 60-kilogram student weighs 600 newtons. He does a bungee jump. Calculate the change in gravitational potential energy as the student falls 50 meters. Give the unit. So I'll write that my mass is equal to 60 kilograms. That my weight is equal to 600 newtons. I'm including everything, and my distance is 50 meters. And it's asking me for gravitational potential energy in joules. I don't know. I want to find gravitational potential energy. I'm going to remember to myself that gravity is 10 newtons per kilogram. I've collected all my terms. Distance, height, same thing, except height goes up and distance goes across. I have everything I need to find my gravitational potential energy using the equation m times g times delta h. The EP then is equal to 60 times 10 times 50. Pop that into my calculator. And the gravitational potential energy is 30,000 joules. So you get 1 mark for this, 1 mark for this, and 1 mark for showing you're working out. Steel ball has a volume of 3.6 centimeters cubed. Volume is equal to 3.6 centimeters cubed. Do I need to turn this into meters cubed? Yes, I do. That's going to be really, really fun. And a mass of 28 grams. Mass is equal to 28 grams. Do I need to turn that into kilograms? Why, yes, I do. Look at these units. They want them in kilograms per meters cubed. Calculate the density of the steel in kilograms per meter cubed. Now, I'm going to go to, I'm going to change this back into meters. And to do that, I've got to multiply by 10 to the minus 6. Okay, it's not to the minus 3, because I'm not just going from centimeters cubed to meters cubed. I'm not just going from centimeters to meters. I'm going from centimeters cubed to meters cubed. So I'm going to put that number down there as 3.6 times 10 to the minus 6 meters cubed. I'm going to divide 28 grams by 1,000, and that's going to give me my mass is equal to 0.028 kilograms. And I'm going to put them into my equation to find my density in I don't know how many kilograms per meter cubed. Density is equal to mass divided by volume, meaning that my density is equal to 3.6 times 10 to the minus 6 divided by 0.028, giving me my density equal to 7777. That can't be right. 777. Yeah, okay. 777. Lots of sevens. I'm going to leave that as just 777 kilograms per meter cubed. The steel ball is at room temperature of 20 degrees Celsius. So the temperature, that's time, pardon me, incorrect, second mistake. Yeah, the temperature is equal to 20 degrees Celsius. It is then put in a pan of boiling water, maintained at 100 degrees Celsius. Oh, right, okay, so that's going to be theta 1, temperature 1. Theta 2 is going to be 100 degrees Celsius. Calculate how much thermal energy we're looking for Q, and I don't know how many joules. The ball gains as its temperature increases from 20 degrees Celsius to 100 degrees Celsius. Delta theta change in temperature is equal to 80 degrees Celsius. 100 take away 20. The specific capacity of steel C is equal to 510 joules per kilogram degrees Celsius. I'm going to look at my little sheet, and I'm going to see that the change in thermal energy is equal to M times C times delta theta. I'm going to put my numbers in. Delta Q, you can rearrange first or you can substitute first. I don't really care. I'm going to do my my rearranging first just because it's what I do. Do I have to? Oh no, sorry, I don't have to do any rearranging. It's just asking for that. So delta Q is equal to the mass. Where do I get my mass from? Well, it's a volume of this and a mass of this. I've already worked out my mass to be 0.028 kilograms. So I'll put that in here, 0.028 times specific heat capacity, joules per kilogram. I don't have to do anything fancy with that. Multiplied by the change in temperature, which is 80. Pop that into my calculator. And I've just messed that up. Hang on. 0.028 times 510 times 80. Give me an answer of 1142.4, or if you want to round it up to something a little bit more useful, 11,000. Next question. The distance between the Earth and the Sun is 1.5 times 10 to the 11 meters. So distance is equal to 1.5 times 10 to the 11 meters. Don't need to do anything with that. Light takes time of 500 seconds to travel from Earth to the Sun, and the wavelength of light is 670 nanometers. All right, so I'm going to be changing that in just a wee second into meters. Calculate the frequency of red light using only data provided. That's very fun. That's a good question. All right, so if I'm going to convert this into nanometers, then I'm going to have to divide that by 10 to the minus 9, multiply that, pardon me, by 10 to the minus 9. So I'll just keep that as my little in the side there. So it's going to be 670 times 10 to the minus 9 to convert from meters to nanometers. But there is no equation that links wavelength, distance, and time to find frequency. Instead, I have got this equation: velocity is equal to frequency times wavelength. I could, if I wanted to, do a velocity divided by a wavelength equal to frequency, but I don't have a velocity. I can use distance and time to find that, though. So velocity is also distance divided by time. Velocity would be 1.5 times 10 to the 11 meters divided by the amount of seconds it takes to arrive at Earth, meaning that my velocity is equal to 1.5 times 10 to the power of, not squared, the power of 11, divided by 500, giving me 300 million. So we're giving this a nice round answer here, 300 million meters per second. 3 times 10 to the power of 8, that will be, so I'm going to write down that my velocity is equal to 3 times 10 to the power of 8 meters per second. And now I can substitute in 3 times 10 to the power of 8 divided by the wavelength, which is 670 times 10 to the power of 9, giving me my answer, 3 times, okay, so I'm going to use my a over b function here, press a over b, 3 times 10 to the power of 8, down I press down, 670 times 10 to the power of minus 9, giving me an answer of, hello, yes, okay, 4.47 times 10 to the power of 14. Now, the way that was written on my calculator was this: 4.4776114 E14. E14 just means times 10 to the power of whatever number comes after it. Lovely stuff. The rock falls off the top of a cliff of height h. H is equal to h, I don't know, meters. Figure 1 shows a rock falling. Oh, look, there's a rock. The Earth exerts a force of 100 newtons on a rock, 150 newtons. The work done by this force when the rock falls from the top to the bottom of the cliff, from the top to the bottom of the cliff, is 2,700 joules. 2,700 joules is my work done. Calculate the height of the cliff. Okay, I'm going to use E is equal to F times D, because a distance is just the height that goes along the ground. So I can find h from here. I can rearrange my equation. I'm going to divide across by f. E divided by f is equal to d. Distance is equal to 2,700 divided by 150. Putting that into my calculator, it is divided by 150, 18 meters. I don't have to do anything with my units. They all match up. Newtons, joules, everything's great. State the value of the kinetic energy of the rock just before it hits the ground. Now, this is a state, not a calculate, so we don't have to do any calculations. But if my rock has done 2,700 joules of work from the top of the cliff to the bottom of the cliff, that means that it would have had 2,700 joules of kinetic energy at the top, meaning, gravitational potential energy at the top, meaning it will have the exact same amount of kinetic energy at the bottom. So all I have to do is figure out the amount of work that was done, the kinetic energy, work done, the same thing, 2,700. The mass of the rock in figure 1 is 15 kilograms. Mass is equal to 15 kilograms. Calculate the velocity of the rock just before it hits the bottom of the cliff. Velocity is equal to, I don't know, meters per second. I have got the kinetic energy, EK, is equal to, let me just move this down a little bit because now I've got all my numbers. EK is equal to 2,700 joules. And my equation is EK is equal to 1/2 times mass times velocity squared. It's asking me velocity in meters per second. I've got no strange units. So velocity is equal to the square root of EK over 1/2 times m. Just substitute my numbers in. 2,700 over 1/2 times 15, giving me, so I want to press my squared button, my A over B button. I'm going to write 2,700, and then I'm going to divide that by 0.5 times 15. My answer is 18.9737 meters per second. I can put that in as 19. Question 10, 9, whatever question this is. Ball is a mass. Mass is equal to 0.046 kilograms. Calculate the change in gravitational potential energy when the ball is lifted through a vertical height of 2.05 meters. Remembering that G is equal to 10 newtons per kilogram, and it's asking us to find the amount of kinetic energy. EK is equal to I don't know how many joules. EP, pardon me. EP is equal to M times G times delta H. EP is equal to the mass 0.046 times 10 times 2.05. EP is therefore equal to times 10 times 2.05, giving me an answer of 0.943. Now there's 3 decimal places there, so we can leave it as 3 decimal places here as well. The ball is released. Oh, good for it. We don't want to keep our little laboratory equipment in a cage, do we? Calculate the kinetic energy. So it's asking me to find EK in joules of the ball when it had the speed of 3.5 meters per second. Velocity is 3.5 meters per second. Now I have the mass of the ball from the top of my question, so I must always RTFQ, read the full question when looking for numbers. And I'll write down my equation. EK is equal to 1/2 times mass times velocity squared. EK is equal to 1/2 times 0.046 times 3.5 squared. Put that into my calculator. 0.5 times 0.046 times 3.5 squared. And again, please don't forget the squared. It's a really common mistake. 0.28175 joules is your answer. We have the 3 decimal places there, so I'm going to go 0.282. Figure 8 shows 2 ice skaters during a performance. Aren't they marvelous? The 2 ice skaters are traveling together in a straight line at 3.5 meters per second. V is equal to 3.50 meters per second. Oh, this is interesting. The total momentum is 371 kilogram meters per second. The man has a mass. Ooh, man has a mass of 64.5 kilograms. What is the mass of the woman? Right. Interesting. So these two have got a mass. I'm going to call this mass total. The mass of the man, mass M, is equal to 64.5. Mass F, mass female, is equal to I don't know how many kilograms. So M total will equal MM plus MF. Now, I have got the total momentum of both of those people. So momentum, 371 kilograms, is for M total, for the total amount of mass. So if I do momentum is equal to mass times velocity, and I divide across by V, I can find the total mass of the pair that are skipping across the ice. So I'll put my momentum in, 371 over 3.50, to get me my total amount of mass is equal to M total. We're not done there, so we'll do 371. This is a really nice question. Divided by 3.5 will give me 106. So 106 equals M total. And so what I'll do is 106 minus 64.5, pardon me. And 64.5 will equal the mass of the female. 106 take away 64.5 will equal 41.5. 41.5 is the mass. Now that is worthy of a 4-mark question. Calculate the kinetic energy of the man. The mass of the man is 64.5 kilograms. The kinetic energy, EK, I do not know, but it is measured in joules. And the velocity of the man is 3.50 meters per second. Put that into my equation of EK equals 1/2 mv squared. And then I can put my numbers in. 1/2 times 64.5 times 3.5. If anybody's listening to this, say the secret password, cheddar cheese on my knees, ha ha ha, and you shall receive 20 achievement points. Now, I'm going to pop this into, and don't tell anybody else, all right? Cheddar cheese on my knees, ha ha ha. Say that to me in a private location where no other year 11s can hear you, and you shall get 20 achievement points. Almost forgot my square, didn't I? Almost forgot my square. 0.5 times 64.5 times 3.5 squared is equal to 395.0625. 395.0625. And we got any, did we just get, hold on, we went to one decimal place there, so I should do the same thing. 395.1. A beaker contains 0.25 kilograms of water. 0.25 kilograms of water at room temperature. The beaker of the water is heated until the water reaches boiling point of 100 degrees Celsius. The specific capacity of water is 4,200 joules per kilogram degrees Celsius. The total amount of energy supplied to the water is 84,000 joules. Calculate the temperature of the water before it was heated. Right, so we're trying to find the temperature of the water before it was heated. Okay, we're going to find the delta theta, the change in temperature, in degrees Celsius. Using the equation Q is equal to m times c times delta theta. I am going to rearrange this. Q over m times c is equal to delta theta. I shall put my numbers in. I'm going to have to switch this in a little bit. 84,000 divided by the mass, which is 0.25. Times specific heat capacity, which is 4,200. I'm going to pop that is equal to delta theta. Pop that into my equation. 84,123 A over B. 0.25 times 4,200, giving me an answer of 80 degrees Celsius. Delta theta was equal to 80 degrees Celsius. Now, delta theta will equal theta at the end added to theta at the end, take away theta at the start. So I had the change in temperature, which is 80. No, sorry, pardon me. Well, yeah, change in temperature was 80. I'm going to take away the start temperature, not add it to it. The end temperature was 100, and the change in temperature was whatever that number was. Sorry, bit of confusion there. To be honest, I was just trying to remember what the password was, and I can't remember it. So the change in temperature will be the end temperature, take away the start temperature, meaning the start temperature was 20 degrees Celsius. The heating continues until 0. And also, please make sure that you do this a little bit neater. It's very difficult writing with a mouse, so just bear with me. The heating continues until the mass 0.15 kilograms of the water is turned into steam. The thermal energy needed to turn the boiling water into steam, Q, is equal to 0.34. Megajoules. Sneaky little hobbits trying to get us confused. That's a megajoule, not to be confused with a millijoule. Okay, it is not that. It is a million joules. So I'm going to multiply this by 10 to the 6. 0.34 times 10 to the 6 is 0.34 times by a million. Calculate the specific latent heat of water. L is equal to, I do not know how many megajoules per kilogram. This is why we write down the units, because if it's asking us for megajoules per kilogram, I am not to do this I'm not to change the megajoules into joules. So they were doubly sneaky little hobbits. Q is equal to mass times specific latent heat. Q divided by M, divided across by M, is equal to L. I shall write down that 0.34 divided by 0.15 is equal to my answer, which is L per kilogram. Yeah, divided by 0.15. Sorry, just doing a double check there. It's always good to do a double check. Why is this not sitting happy with me? What is it? It's not 0.2. Yeah, okay. Do you know what? It is what it is. Specifically, specific latent heat is 2.26 megajoules. Oh, that's why, because it's in megajoules, of course. 2.26 megajoules per kilogram. 2.3. 2.26. Oh, 2.6. 2.7, I'm going to call it. Pardon me, folks. I'm so indecisive. 2.2667, 2.27. Figure 4 shows a drone. A different drone has a mass of 4. How are you going to show us this one if you're not going to show us the other one? 4.5 kilograms. The drone rises from the ground to a height of 20 meters. Calculate the change in gravitational potential energy. Delta EP is equal to I don't know how many joules. It's asking us in joules. And the gravitational field strength is equal to 10 newtons per kilogram. EP is equal to m times g times delta H. Oh, what is going on there? Yeah, do you know what? Half an hour in, that's why, times delta H. EP is equal to 4.5 times 10 times 20. Pop that into my calculator. 4.5 times 10 times 20. 900 joules. That's right. EP is equal to 900 joules. State the amount of useful work done with the blades as the drone rises through 20 meters. Well, if the drone stopped down here and went up there, and it has gained 900 joules of gravitational potential energy, then there must have been 900 joules of work done to that drone to give it those 900 joules. Work has transferred those 900 joules from some store into that store, so the amount of work done was 900 joules. All right, I'm going to take a little pause there. Every time.